I'm Dr. Robert Lopez, and today I want to talk about some glacial erosional and depositional features. In fact, first I want to look at the depositional features over here, and note that I have an image here of an alpine glacier with the head wall up here. The cirque is basically an erosional feature that I'll talk about in a little bit. That it's where the head of the glacier exists, and it's really more of an amphitheater type bowl-shaped depression that's formed by the glacier. So, but the thing about the glacier, remember, it's moving till. Till is frozen in the ice. The material is moving down, and we're going to make some moraines, some depositional landform. And really, they're ridges that form either on the sides of the moraine or at the end of the moraine here. And there could be even some that form in the middle of the moraine. And I'll explain how those form in a moment. So we talked about till and moraine already, but there's going to be 4 types of moraines. And so the lateral, medial, terminal, and recessional. So we've already talked about these two. Well, let's talk about these. In fact, before I even go back to this picture, let me just show you an image or draw you a little cartoon of what a valley cross-section may look like. So in a glacial valley, it's going to be pretty wide. It's going to be a U-shaped valley, something like this here. And the ice will exist with some crevasses in here to a height near the top of the valley, but not going over the top here. And then what will happen is it'll leave glacial debris along the sides here, and you'll make a little ridge of glacial till, which will make a moraine there, and there'll be another ridge here, and then it'll kind of taper off to the bottom here. So all this will be composed of that till and leaving this ridge-like fashion. So when the ice melts away, so we'll look at another image of this here. Now we'll have our valley here again. Now the ice is gone, the glaciation has ended, but we still have these ridges on the side here. There's one there, and then there's another one that occur over here. And so these would be full of till, full of that debris that was plucked, carried, and dropped off by the glacier. So these would be the lateral moraines, left lateral, right? So they occur on the sides of the moraine. But the key thing, it is a ridge that's formed, and I'll show you some pictures of those in a little bit here. And so now going back to our picture here, you can see in this image here we actually have ice. And we're seeing lateral moraines being formed at the side here, right? So this would be the lateral moraine, where a tributary glacier may join the main glacier that's coming down here. You would see, because here there's a lateral moraine there and a lateral moraine here, but when the 2 lateral moraines join up here, these 2 here join up from this tributary glacier, what will happen, they'll make a medial moraine. So the medial moraines form when a tributary glacier joins the main valley glacier here. Another feature that this image is showing is when, just like there are waterfalls, when an ice goes over a steep cliff or an escarpment, what will happen is the ice will fracture and make these kind of precariously perched blocks of ice in here, and it's called the ice fall. And then some of them do tumble down, so because the ice is cracking. Remember, this is occurring in that brittle zone here. Another feature here is this feature here called a Nunatak. So if the glacier ice, or if in this case a peak is high enough where it sticks above the glacier ice, you'll make something called a Nunatak. So a Nunatak is a feature that hasn't really been glaciated. And here's a image. This is a Tuolumne Meadows region, what it may have looked like during the last glaciation about 20,000 years ago. And you can see Cathedral Peak here would be an example of a Nunatak. And some of these other peaks as well, like Matthey's Peak over here. So those would also be examples of Nunataks that would be sticking above the ice field there. All right, so we talked about the moraines there. Now let's look at some erosional features related to glaciation. So this is what are really more important, because this is what we see today. Most of the glaciers have melted back. We don't see the glacier. So one feature that we do see are these cirques. And cirques are commonly amphitheater type shape, bowl shape. They occur at the head of the glacier, basically where the head walls begin. So we discussed those are bowl-shaped already. So the cirque would be up in here. When the glacier melts, usually there's a little lake that's left up there, and those little lakes are called tarns. So a tarn is a small lake that occupies the cirques. Now, sometimes, in fact, I don't have it up here, there are these Paternoster Lakes. And what these are, they're basically, they're also called rock basin lakes. You might see a string of lakes. As the glacier melts, there'll be several areas where water can pond up. So these are basically a string of tarns. And I'll show you some pictures of these when I show you the PowerPoint. So a string of these tarns going down the mountain here. Another important feature is the arête and the horn. So we'll talk about these in a moment here. And so when cirques meet head to head, these features form. In fact, if two or more cirques, so here's a cirque here and here's a cirque here, note that these two are meeting, then you're gonna get this really jagged ridge here. And this jagged ridge is called an arête. So an arête is a jagged knife edge ridge between two cirques. Now if you get two or more cirques join, or sorry, three or more cirques forming here, 1, 2, and let's say there's one behind this peak over here, you'll get a horn. So a horn is a faceted peak formed where three or more radially dispersed cirques meet, right? And so remember the arête has two, the horn will have three. And a col will be a low saddle in the arête. So for example, right in here, you can think of this as a col. It's sort of a pass, a low saddle. In fact, here's a good one up here. It's even labeled as a col right here. So if this is an arête up here, you have a col right in here, a low saddle in the arête. One feature we find is that glacial valleys are always going to be U-shaped valleys because the glacier widens out the valley, makes it a flat valley floor with steep-sided walls, right? And what will result for that is if there's a tributary stream that was joining that valley, well, then that tributary stream is going to be undercut. And when it enters the valley now, it's going to enter at the vertical cliff. It'll be a drop off. So these are streams or tributaries to the original valley. They now stand high above the valley floor, creating waterfalls, right? So a good example of this one is Bridal Veil Falls in Yosemite. So in fact, let's look at a little sketch here. So when rivers form, rivers usually form something that's called a V-shaped valley. Something like this here, like the Colorado River is a V-shaped valley, so the river would be down there. But glacial erosion is gonna take this and make this into a wide valley called a U-shaped valley there, right? So there's a U-shaped valley, making it wider. So if there was a tributary river that would flow down here in the past, now that tributary river that comes here is going to make spectacular waterfalls here, and these would be the hanging valleys here. Hanging valley would be this feature right here. And so I'll show you again an image of that in a moment. Other landforms left behind by the glaciers are these roches moutonnées. And roches moutonnées is a French word for rock sheep. And so they're smooth, humpback, granitic mounds sculpted by the overriding glacier. So for example, let's say we have a mound of granite, and they'll be kind of jagged on one side here. A good example of one of these is Lembert Dome in Tuolumne Meadows. So what's happening here, because the ice was flowing in this direction here, let's say this is ice coming over here, as it flows, it's gonna smooth the backside. It's gonna polish this backside, but then what it's gonna do over here is gonna pluck rocks from the front side, so it makes this jagged end. So looking at roches moutonnées, they tell us a couple of pieces of information. One, they show us which way the ice was moving and where the plucking was occurring here, right? So it shows the ice direction there. Other features that are common in glaciated landscapes include the striations produced by moving glacier, and really they're dragging the rock fragments, the sand, the silt, scratching and grooving the bedrock. And they also point to the flow direction of the ice. So there's a couple of pictures of that in your textbook as well. And then glacial polish, because the rock is being ground into a fine powder what happens, well, the scratching action of this fine material will polish the rock and make this really nice glacial polish. Where you see the scratches in the polish, those would be the striations. And then the last feature here are these glacial erratics, and what they refer to boulders that seem out of place, because what happened is the glacier plucked them from higher up in the valley, brought them down, and then when the ice melted, it dropped them. Sometimes they're called drop stones, right? So these are glacial erratics that are just dropped by the glacier as it was melting. And usually the rock type or the erratic is going to be different than the bedrock it's sitting on, so which means it has been transported from some other area. In fact, Plymouth Rock, the famous Plymouth Rock, is a glacial erratic, and it was carried from New Hampshire to Boston. And so because it doesn't resemble rocks in Boston, it resembles rocks in New Hampshire. Now, before we talk about the different glaciations in the Sierra Nevada, there's a number of ideas. The most recent one is this last one, these astronomical cycles. And it seems like that Earth orbits the sun, and the way Earth orbits the sun changes on periods of about 40,000 years. The way Earth kind of, as it goes around the sun, the axis sort of wobbles. Like if you have a top and you spin the top, as the top slows down, it starts wobbling, making a cone shape, right? And so that means that the axis is going to point to the axis of Earth will point to different directions, which means that the northern hemisphere and southern hemisphere will have an obliquity. I mean, they're not going to change dramatically, maybe I think as much as 5 degrees, but there is a little wobble in there, and depending on the wobble, it may bring northern hemisphere more solar radiation or less solar radiation in terms of the duration of sunlight or daylight hours affecting that region. But your book says that these Milankovitch cycles may control the timing of the glaciations, right? And these cycles are due to cycles in the shape of Earth's orbit around the sun, whether it's closer or farther, and also that wobbling of the axis, the rotation. And these affect how much heat is received at different latitudes. Remember, the key thing about solar radiation is the duration, how many hours. For example, that's the difference in our seasons. In winter, we see fewer daylight hours, so it's colder. It's not that we're necessarily farther from the sun. It's just that, in fact, in the winter, we're actually a little bit closer to the sun right now. But our angle of Earth's tilt makes us so that we see fewer daylight hours. On the other hand, in the summer, we're actually a little farther from the sun, but we have more exposure to the solar radiation, so we see more daylight hours. So this wobble can coincide with northern hemisphere getting more or less solar radiation. And the key thing, having less solar radiation, but also where Earth would be a little bit farther from the sun based on the orbit of the Earth. So it's a little complicated, but it seems like these Milankovitch cycles do explain at least the timing when these glaciations have occurred in the past.